Welcome back to Physics 142. We've been talking about circuits that have resistors and capacitors in them. And what we figured out last time is that the behavior of a circuit matters whether we're considering it right after you close the switch or after some long period of time. And we realized that right after you close the switch, immediately after you close the switch, so very close to time equals 0, the capacitor ends up acting a lot like a wire, right? Capacitor acts like a wire, whereas after a long time, all right, after a long time, the capacitor acts like an infinite resistor. Right? And basically what that is when we close the switch, immediately lots of current is flowing. Basically all the current is flowing. It really wants to charge up the capacitor, but after a long time, the capacitor is fully charged up. It doesn't want any more charge to flow. It's going to stop any current from flowing. But we can use this to actually analyze circuits and sort of think about what happens with these circuits. So let's consider this circuit here. I've drawn a RC circuit, but this is sort of an interesting one where I now have put a couple of resistors in it. All right, so I have a power supply and a switch, and then I have a resistor, and then a resistor and a capacitor that are in series with each other, but in parallel with this resistor. All right, so how do we think about this one? Well, let's first think about what happens right after we close the switch. So, T just a little bit greater than 0, right? So T very close to 0. What is this going to look like? All right. Well, in this case, we said right after you close the switch, lots of current is flowing, right? All the current flows. Essentially, we can replace the capacitor with a wire. And so that circuit then would look like this, right? Right after it closes, right? What would we expect? Well, we'd have a resistor, and then this resistor here, and then the capacitor is just acting like a wire. All right, so resistor R, resistance R. And this, well, this is just two resistors that are in parallel, right? Because you go along, you have a choice. Hey, it's a split. All right, so these two must be in parallel with each other. All right, and two resistors in parallel. Well, we can calculate that resistance, right? And that was the 1 over equivalent resistance is 1 over R1 plus 1 over R2. And so in this case, if they're the same resistance, we end up that the equivalent resistance is just going to be 1 over R plus 1 over R, which is 2 over R, right? And so we end up with R over 2 is our equivalent resistance, right? And so if we wanted to get the amount of current flowing then, we could say that the amount of current that flows is just the current is going to be V over R, right? V equals IR, so I is V over R, and the amount of resistance was half an R, right? So this is going to be V over R over 2, all right, which is just going to be 2V over R. All right, so in this case, the amount of current that flows right at the beginning is 2V over R because this is acting like two resistors that are in parallel. But now let's think about several time constants later, right? So sort of a long time later, all right? After a long time, then C is going to act sort of like an infinite resistor, right? And so then our circuit would look like this, right? Then the circuit after a long time, right? So T equals, long, right? Some long period of time. Now we again have this resistor R, right? But now we also have resistor R, and that's going to be coupled with a sort of where it's acting like an infinite resistor. Right? And so what's going on here? Well, with an infinite resistor, no current wants to flow, right? So, if we tried to think about the current flowing here, well, we just have essentially 0 current, right? So the current here, 0 current, because infinite resistor won't let any current flow, right? I is V over R. If I, divide by infinity, I get 0, right? So no current's flowing here, but current can still flow through this part of the wire, right? This isn't attached to the capacitor, so you still have current flowing in the circuit. It's just not going through the part with the capacitor, right? And so here we still have current flowing through this resistor, right? And so that's essentially just, you know, a sort of most basic circuit where the current flowing is just going to be V over R, right? So here, the total current that goes through 1, right, is, well, all of it, right? And I is just going to be V over R. If you wanted to think about it a little bit, more mathematically here, the equivalent resistance of these two in parallel, you have 1 over R equivalent is 1 over R plus 1 over infinity, right? Because these two are going to together act as an infinite one. 1 over infinity is just 0, right? And so the equivalent capacitance of this circuit is just R, and so I is V over R. So after a long time, you have sort of a different amount of current flowing than at the beginning. At the beginning, you have current flowing through here and through here. It's going to flow fast, all right? Later, it's going to flow slower, right? You know, we have half as much current, and it's just specifically going to be going through this part of the circuit. But don't get confused about this, all right? Just because you have it acting like an infinite resistor, you can still have current flow in other parts of the circuit, right? It just can't flow in this particular part of the circuit. So you still have to analyze the go through the process of trying to think about what's going on here. So hopefully this is an example that just gives us a little bit more intuition then about how RC circuits work and how we can mathematically approach these RC circuits.